Hey y'all, it's your math teacher, Mr. Boyden, back at it again. I'm excited today because we're going to be starting our trigonometry unit. And this is where we start to get out of kind of the basic algebra stuff and graphing, and we start to get into more of like the meat and potatoes with our trigonometry stuff. So let's start today. We're just going to talk about different ways of measuring angles and understanding angles. Okay, you probably already have a pretty good idea of what degrees are. Like, if I ask you to draw a 90-degree angle on your paper right now, is that something that you're able to do? I'm guessing so, right? Things like maybe letter L or letter T, they make, if I drew it correctly, make 90-degree angles. Or if I asked you to draw a 45-degree angle, is that something you could do? Probably. Okay, maybe you'd have something like that. Okay, what if I asked you to draw a 270-degree angle? Is that something you could draw? Well, we think about it. 270 would be 3 times as big as 90. So if 90 is here, then 180 is there. So 270 is there. We would just notice that 270 is this part of the angle on the outside, not the part on the inside. So we already have that, but what we need to understand as well is what is a radian and how do they connect. So what we do is we start by thinking about the radius, and this is just a general circle. So we have our circle, it has some radius, and watch how this radius is now going to be curved to fit along what's called an arc. It's being bent, sort of. Okay, guys, that's what a radian is. Okay, right there. All it is, it's the angle which produces an arc length that is the same as the radius. So that's one of them. Now, it turns out that it ends up being about 57.295 degrees. You don't have to necessarily know that, okay? And because it's an approximation, we're actually not going to use that in our calculations. Okay, I'm going to let the animation run a little bit further so you can see how this fits around a circle. Okay, so what they're going to do is now they're just going to keep putting more radii going around the circle. So here comes 3. I want you to notice that's not quite half a circle when they stop right there. So half a circle is actually pi radians. And they're going to keep going, 4, 5, 6. And they need a little bit more than 6. So here are the key things that I want you to have. If you're taking notes, you'd want to write these down. Folks, you would want to know that 360 degrees and 2 pi radians are equivalent. Okay, that's the same thing. They're saying all the way around the circle, 360 degrees, 2 pi radians, those are the same. Okay, over here, same thing. Pi radians and 180 degrees are the exact same angle measure. Okay, everything else you don't have to worry too much about. Like all these decimals and things, I wouldn't worry about that. Okay, but those in conjunction with the idea that what is a radian? It is an angle on a circle such that the arc length is the same as the radius. All right, now that we know what radians are, let's practice going back and forth between radians and degrees. What I'd like you to remember is that pi radians, and I'm going to put it rad for short, and that's common. Pi radians is the same as 180 degrees. Okay, and that's going to make these calculations a little bit easier. So actually, the first one just got really easy. 180 degrees, that's the same as pi radians. They asked us to convert our units. So we would just say that's the same as pi radians. Okay, what about 45 degrees? That gets a little bit more technical. Okay, so what we're going to do is use this conversion factor right here, and we're going to multiply and divide by these numbers to figure out what this turns into as radians. Here's how you know what to do, though. Okay, see how right now, like, this is over 1, which means degrees is on top? If I want degrees to cancel out in this calculation, I need to then put my degrees in the denominator. And I know it might look weird at first if you've never seen it before, but we actually can cancel off the units now. Okay, now 180 on top, I'm going to put pi and rad. And before we type this in the calculator, I want to stop and just talk about this for a quick second, because people think it's kind of weird, like, wait, you can multiply by pi and divide by 180? Actually, no. What I'm doing is multiplying by 1. Because, guys, remember, pi radians and 180 degrees are the exact same thing. And any fraction in which the top and bottom are the same quantity, it has a value of 1. Anything divided by itself is 1 is how we normally say that. Okay, so actually, I haven't broken any rules here, and I've just multiplied by a really funny form of the number 1. So here's what this does. Now our units are radians, so I'm going to put rad here. I already know my units. I'm going to simplify 45 over 180, recognizing they're both divisible by 45. So that's the same as 1/4. And then I'm going to leave the pi as is. Now you may be tempted to type the pi in a calculator. We're not going to do that. We want an exact form, and we don't want all kinds of crazy trailing decimals and things like that, so we're going to leave that alone, y'all. That's actually done. Okay, let's keep going. Pi rad, that's a quick one. That's the same as 180 degrees. We already knew that. And what about pi over 2 radians? All right, we're going to do that same trick with a conversion factor. Okay, we have radians here, so I want to divide by radians. I'm using this information. Pi radians is the same as 180 degrees. All right, now here's how we simplify this. We first notice radians on top, radians on bottom, they cancel out. Pi on top, pi on bottom, they cancel out. And so what I have is 180 divided by 2. So this is the same as 90 degrees. Okay, and that's all the conversions are. So even if you get weird looking numbers, you're just going to write down your conversion factor, and there's only 2 of them. It's either pi rad over 180 or 180 over pi rad, and then you're just going to simplify. Okay, that's all it is. All right, let's talk about arcs. And I'm not talking about Noah. I'm talking about circle arcs. All right, so guys, an arc is just a portion of the circumference of a circle. Now, when I say circumference, what we're talking about is the outside of the circle. Let's do an example. Let's consider this circle here with a radius of 5 inches. I'm going to draw that in. We want to know the length of a 90-degree arc. Let's make a 90-degree angle. Best of our ability. The arc is this out here. Okay, it's that curve. It's the part when we saw that animation that the radius became the arc, that part on the outside. Okay, so we're being asked, how long is that arc? Now, they're not asking degrees. We're actually being asked a literal distance. They're saying, hey, this is 5. How long is this? Like if you had a curved tape measure, how long would that be? So guys, here's what you got to think of. If it's part of the circumference, let's first remember what a circumference is. 2 times pi times the radius. And this is part of that. So here's how I go about my calculation. I'm going to start with 2 pi r, and we know that r is 5. We were told that. And I only want part of that. How much do I want? I want 1/4. 90 degrees is 1/4 of the circle. Now, so this will work later. I'm going to write it as I want 90 degrees out of a grand total of 360 degrees. That's the proportion of the circle that I want. So I'm actually going to now go to my calculator and see what this is. Okay, so I'm typing in, I'm going to do 90 and times 2 and times 5, and we're going to divide that by 360, and then we're going to multiply that by pi. I'm going to make a quick note. That turns out to be 2.5 pi, and so I actually want to approximate that because I want to know how it compares to 5. So 2.5 times pi, and please use an actual pi button on your calculator. Don't type in 3.14. We want this as accurate as possible. So what do I get? I get 7.85 inches when I do that. Now ask yourself, does that seem reasonable? Does it look like this curve is longer than one of these straights? Yeah, I think it probably does. Does to my eye. So yeah, that seems like a reasonable answer. So that's 90 degrees. What about 73 degrees? This would be a great time for you to pause the video and try it on your own. So I encourage you to do that. When you're ready, hit play. Okay, here's all it is. Same old deal, same old circle. So it's still 2 times pi times 5. But we're not multiplying by 90 over 360 because now we have a smaller arc, 73 degrees. So we're doing 73 over 360 is what we're multiplying by. So let's type that in. And this time we should expect a smaller answer. I'm getting a smaller answer when I do that. I'd like you to calculate it as well and make sure you can get this. 6.37 inches. All right, so if you're feeling good, we have a secondary question down here that you could try to answer. Okay, let's go through it. Janie cuts a slice from a circular cake. Hey, that sounds like fun. She's eating cake. The radius of her slice is 4 inches. All right, so radius is 4 inches. And the arc is 5 inches. So there's some sort of a slice where we have 4 here and 5 there. We would like to know the central angle. All right, y'all, I'm going to introduce you to a new symbol right here. It goes like this. Okay, it looks like 0 with a line through it, kind of. Okay, and this is called theta. And theta is a Greek letter that's used to describe angles. Okay, it's always angles. And so what that's going to do here, it's going to describe our central angle. So I'm going to put it in there. And sometimes I extend the line through so it kind of looks like the planet Saturn. That's totally fine. If you're going to make it look like the planet Saturn, please know that it has horizontal rings if you're doing it that way. It's not, so it's not this symbol. That means something different. Okay, it's not that. If you wanted to extend it, it's horizontal, so it's like that. That's our theta. Let's get that out of here so you don't get confused. Okay, so now we're going to try to figure out what is that central angle. All right, so let's go with what we know. Last time we dealt with arcs, we had central angles and we had radii. Same three things here, we're just missing one of them. So here's all we're going to do. We're going to say, how would I find that number, that 5, if I didn't know it needed to find it? Exactly what we did a minute ago. I'd say 2 times pi times the radius, and I do know the radius, that's 4. And we would multiply that by whatever our angle is, theta, just like we did before, 90 or 73 over 360. Okay? And when we did that, we would expect that our answer was 5. So now we have a perfectly workable equation here. Okay? So see, we're actually going to be able to get this. So here we go. Let's see what we can do. It looks like I have 2 times 4. I'm going to call that 8, so I'm actually going to come over here. And let's zoom in so I have a little more space. You have the luxury of going down the page. I run out of space on my page. Okay, and so what I'm going to do is I'm going to notice that I have theta over 360, and I actually have 8 pi sitting right there. So that's multiplied by 8 pi equals 5. Now, I'm not super fond of the fact that it's multiplied by 8.5 because that's in the way of theta. So what we'll do, I'm going to divide out the 8 pi on both sides. So I get theta over 360 equals 5 over 8 pi. And then I'm going to multiply both sides by 360 to cancel out that 360 right there. And now it's calculator time. We've solved this thing for theta. Off we go. So 5 times 360, divide that by the quantity 8 pi, and I get 71.6. Theta equals 71.6. Now, we have to answer the final question here is, what we just found, is it in radians or is it in degrees? Okay, guys, here's how you can tell. The way we set up our calculation, we said that it was out of 360. When we said 360, do you think we were referring to radians or degrees? Definitely degrees. Okay, and so we just found this answer in degrees. Now, if they asked for it in radians, which they didn't specify here, but if they asked for it in radians, we would need to either convert this number or use a different technique that would find it. But for now, we know. So it looks like she had a pretty good size slice of cake there. 71.6 degrees is a pretty hefty slice. That sounds like the kind that I would probably cut for myself, knowing me, but there it is. Okay, now with that, let's talk about sectors. Now we actually have a sector sitting on the screen here. We just haven't talked about it yet. So an arc is that outer portion. Okay, you could think about it like if you're eating pizza, it's the crust. Okay, it's like asking how long is the crust if you measured it. A sector, that's the whole slice. You wouldn't want to just take an arc. You'd want to take the whole sector. We're talking about the frosting on the cake. We're talking about the cake itself. There's different layers. If there's all kinds of extra toppings or cherries, whatever you're into. Okay, so that's the whole thing. So a sector is basically the name for this shape, where this third side is curved. It's like a triangle, but the third side out there is curved. So we now want to find the area of that slice of cake that Janie cut for herself. So what we would notice is that that's a portion of the total area of the circle. So let's talk about area of a circle. Do you remember how to find that? Okay, that one is pi times radius squared. And guys, if you don't know that, it's time that you do. Okay, it's absolutely time that you get that down, because what we're going to realize is very similar to our logic before, where the arc was a portion of the circumference. The area of a sector is just a portion of that thing. Okay, so here we go. Pi times, let's see, what was the radius? Radius was 4. So pi times 4 squared. We only want part of that though. Okay, and we now know that she had a 71.6 degree slice. So we're going to use 71.6 out of the whole cake at 360, and we're going to type that in, and we're going to approximate in square inches. What was the area of her slice? Okay, so 4 squared times pi times 71.6 divided by 360, and I get 9.997. If I round that to the nearest tenth, it's actually 10.0 square inches. Okay, now guys, if you're not sure why it's square inches, if you notice right here, that number 4 was inches, and it's inches getting squared. Inches squared, or square inches. Okay, now that's all it is. Okay, so we've found that portion of the total area, 10 inches. They'll get to where they look a little bit harder, but that's the base concept, that anytime you get confused, I want you to kind of come back to that and gain a little comfort in the fact that that's all the concept is. Now, there are two formulas, or two formulae, as we could say it, that are given to you by IB, and here they are. Okay, S is actually an arc length equation, so let's annotate that. Arc length. And we have one for sector area, and I'm going to label that as well. Okay. And it is important that you understand that these formulas only apply when theta is expressed in radians. If you're talking about degrees, these do you no good. Well, you could convert to radians, but these formulas are specific. I want to show you why. Okay, so it's really, really nice if we know formulas. It's really a lot better, though, if we understand formulas. That way, if we forget them or if we make a mistake in them, we can figure out what the mistake was and we can figure out how to fix it. Okay, so for arc length a minute ago, what we had said is that it was going to be theta, or the angle out of 360. But if we're dealing with radians, a circle doesn't have 360 radians. It has 2 pi radians. And then we multiply that by circumference, so 2 times pi times r. And if you notice, the way this simplifies out, you have a 2 pi in the denominator and a 2 pi in the numerator. So good night, you have theta and r left over, which you'll notice is the same as r theta. So that's where that formula is coming from. Okay, it's not totally out of the blue. It's based on taking a portion of the circumference. Okay, this one works the exact same way. If you want to challenge yourself to derive it on your own, that'd be really neat. If not, that's okay too, up to you, but pause now if you want to derive it on your own. For area of a sector, what we said was we would take theta out of that portion of our circle. In the previous example, we used 360 because we were using degrees, but if you're using radians, it's out of 2 pi. And then that's out of the total area of a circle, pi r squared. Let's see how that simplifies. You have a pi on top and a pi on bottom, so those cancel. And then you have an r squared left over and a theta left over, and it's over 2. Now I've written it a little bit differently than the formula, but I want you to notice it's the same. R squared theta divided by 2 times a half. Those are the same thing. Okay, so that's where those are coming for. So now that we sort of have those sitting in our back pocket, let's look at an IB exam style question, or just a general test style question, so we can practice what we've learned so far. Okay, and here's our question. This would be a really good time to kind of pause the video and see how well you're understanding what we've learned. As you know, I'm going to go through it here as soon as you hit play, so whenever you're ready. First thing to notice is this 1.4. Y'all, it's not degrees. Now down here they tell us it's radians. Even if they didn't, you should be able to figure that out because it's not labeled as degrees. It is labeled in here as an angle, and it wouldn't make sense if this picture had a 1.4 degree angle based on the fact that it looks like it's almost 90 degrees. Okay, so first of all, we're asked for arc length ABC. I think I'm going to show my work over here so I have more space. Now, we just talked about arc length. We said that S equals R theta. Hold up. Are we allowed to use this formula right here? It said it only works for radians. We have radians, so we're all good. Let's do this. So that would be radius. They told us that was 8 times theta. They told us that was 1.4. So I'm just grabbing my calculator. 8 times 1.4. And I get 11.2. Now, we are going to be expected to use units. So arc length is a linear measurement, which means it's nothing squared. And right here, we're told that they're using centimeters. So this is 11.2 centimeters. All right, that's done. Let's go to the next one. Find the area of the shaded region. Hey, that's exactly what we just learned. Nice. So what do we know? We know that area of a sector equals 1/2 r squared theta. Do we have that information? Yeah, we do. Let's plug it in. 1/2 times r squared. R squared would be 8 squared. And theta is 1.4. So, guys, I'm just going to go to the calculator. So 8 squared, that's 64. And we'll divide that by 2. And we'll multiply by 1.4. And so I get 44.8 when I do that. All right, we need units. It's an area, which means it's going to be a squared unit. Our units are centimeters. So it's going to be square centimeters. So that's our basic introduction. We're kind of learning base skills that are going to be useful in trigonometry. We actually haven't done trig yet, but we will be doing that very, very soon. So hope you enjoyed this video. Hope it's helpful, and we'll see you next time.